All right. So if we want to find the critical values and the points of inflection and the maxima and the minima and all that for natural log of x squared minus 1, first thing we want to think about is what the domain of this is. And so we know that you can't take the natural log as something that is 0 or negative. So that tells you that anything that is part of the argument of the natural log, that means something inside the parentheses on the natural log, has to be greater than 0. So this is our domain to start off with. That the domain is x squared minus 1 is greater than 0, which tells us that x squared is greater than 1, or that x is greater than 1, or x is less than negative 1. So that's the first and most sort of important piece of this that we got to recognize, because when we go through here and try to get our critical values, we're going to find that many, if not all of them, fall in the pieces where this function doesn't exist. So we'll find our derivative, y prime. And so this is natural log of u. So that should be 1 over u times the derivative of u. And the derivative of x squared minus 1 is 2x. So our derivative is 2x over x squared minus 1. And so if we're looking for when does that equal 0, that's if the numerator equals 0, right, which will be 2x equals 0 or x equals 0. And it's undefined if the denominator equals 0. Which would be x's plus or minus 1. So we can see that all three of these values that could be critical values actually fall in pieces of this function that don't exist. And so we have no critical values for this function. And I think, was I asking you guys to graph or just figure out if it was increasing and decreasing in the maxima and minima?
Not graphing.
Not graphing, okay. Cool. So if we then make a sign chart, it's kind of a weird sign chart because everything inside of here between -1 and 1, we don't really care what's going on. I mean, we can't plug in a number anyway. We can plug a number into our derivative, but it's not going to matter because our function doesn't do anything, right, in that interval. So we'll just plug in something that's more than 1 and something that's less than -1 to see what's happening on the two intervals where it does exist. Does that make sense to everybody there?
Yes.
Yeah. Okay, cool. So plugging in a positive number, like 1,000,000, is going to give us a positive in the numerator and a positive in the denominator, so positive overall. So our function will be increasing. And if we plug in a negative, like -1,000,000, the denominator is still going to be positive, but our numerator will be negative, so we have a function that is decreasing. And so we would say that this function decreases from -infinity to -1. And normally, right, like I said, we put brackets on here, but because the function itself is not defined at -1, we cannot include that point because that point doesn't exist on the function. So we'll put a parenthesis and then union 1 to infinity, same reason for the parenthesis on the 1. If the function existed at -1 and 1, we put brackets on it, but since it doesn't, it stays as parentheses. Good with that so far. I assume I also asked about concavity.
But it's increasing 1 to infinity.
Oh, sorry. Yeah, I don't know what am I doing? Increases from 1 to infinity. Sorry. Thank you. I don't know why I said that it was still decreasing. Clearly it's not. Good or no? All right, and then I did ask about concavity and points of inflection also, I'm assuming. So we had 2x over x squared minus 1 as our first derivative. So to find our second derivative, we just take another derivative. That'll be a product rule. So denominator, derivative of numerator, minus numerator, and derivative of denominator, all over the denominator squared. Everybody good with that?
Yes.
Okay, cool. So then we'll simplify out our numerator. This is what, 2x squared minus 2 minus 4x squared, and then over x squared minus 1 squared. And that becomes what, negative 2x squared minus 2 over x squared minus 1 squared. And we know that y double prime would be undefined once again when the denominator equals 0, right? Which gives us, again, x equals plus or minus 1. And so we know we can't have a point of inflection at those values because our function doesn't exist there. And we'll say that the second derivative is 0 if negative 2x squared minus 2 equals 0, which gives us what? It gives us x squared equals negative 1. So for no values. Right? And so this one doesn't even have any possible points of inflection. We'll just make the same kind of sign chart that we did before, negative 1 and 1, except this time for the second derivative. We don't care about between negative 1 and 1 because our function doesn't exist there. And if we'll plug in a positive number to our derivative, like 1,000,000, this numerator is going to be negative. 1,000,000 squared is positive, but put a negative in front of it, it's going to be definitely negative. And then the denominator is always going to be positive no matter what I plug in because we're squaring it. So negative for this one. And then same thing if I plug in something like negative, negative 1,000,000 squared, it's a huge positive, but when you multiply it by the negative 2, that numerator becomes negative. And then divide by the denominator, which is always positive. So this function is concave down on its entire domain, which is negative infinity to negative 1 union 1 to infinity. Good or not?
Good.
Cool. And so this one's not like, wouldn't be super easy to just graph. You'd have to plug in some points just based on the nature of this function, which is why I didn't ask you to graph this one. But just for the heck of it, real quickly, on Desmos, this is what it looks like, natural log of x squared minus 1. Right? We could find the x-intercepts, right, just by setting the thing inside the parentheses equal to 0. Equal to 1, because that would give us natural log of 1. And then get something that looked like this, approaching some vertical asymptotes at negative 1 and 1. Always concave down, right? This is concave down. This is concave down, but decreasing and then increasing after that gap in the middle from negative 1 to 1. Good or no?
Yes.
All right. Anybody else have any other questions on that or anything else from the homework or anything just in general?
How do you determine if a local minimum or maximum is also absolute?
Okay, so it just sort of depends on the function that you're looking at and what's going on with that function. So I'll try and give you a couple examples here. You go back to here. So suppose I have a function that my first derivative sign chart looked like this, let's say. And we found that, let's say this was, I don't know, it doesn't really matter. Let's say this was 0, this was 2, and we said we had a local max at x equals 2, right? Well, in this particular one, we would know for sure that that local max was also absolute because we were never decreasing again. So this is always going up and up till I get to here, right? And then I'm going down after that. So, I mean, my function just looks, it may have something weird happening here, like a point of inflection or something. But on both sides of that max, it's always going down, right? or vice versa, if this was like a minus and a plus, we would know that that would be an absolute min. What makes it a little more tricky is when you have things. Does that make sense? Like for that one, for example?
Yeah, so you basically just use common sense.
Yeah, but the problem with common sense is, I'll say something mean. The problem with common sense is that most of you don't have any. Ha ha ha. No, I'm just kidding. That's the kind of thing I would say. That's the kind of thing I would say if we were in class and I wasn't recording and I would really mean it. But right now we'll just pretend like I don't mean it. Since I'm recording this, and we don't want the world to know what a horrible person I really am. So what we need to do is, suppose I have something like this, where it's a little less certain. So we have a local max at, I don't know, we'll just say -1, and we have a local min at +1, right? And so this function could do a lot of different things here. It could be increasing and then decreasing and then increasing, and then so that this local max is not an absolute max because I'm increasing beyond it. And this local min is not an absolute min because I'm decreasing beyond it. But this function could also look like this, where maybe I have some sort of asymptote in here. And so I'm still always increasing, just very slowly from -infinity up. And then I hit the local max, which is an absolute max, drop down to an absolute min, and then always be increasing, just increasing up to that asymptote. So it's a little more ambiguous here about whether they're local or absolute max, just from the sign chart. So what you then need to do is you have to check the in behavior. And so, suppose our function is just like, a cubic function. Well, a cubic function, we know, increases without bound, it decreases without bound. But if you throw something else weird in there, like an e to the x or a sine x or just some other weird function that doesn't make it a nice polynomial, then that in behavior could be changing. It may not be increasing to infinity and decreasing to -infinity. And so you have to check what's happening. Is it approaching an asymptote that is, below this local max, and approaching a asymptote that is above the local min? You might have one of each, or you might have a situation where it does something like this. So this is, we'll say this is going towards an asymptote to -infinity. We could have this, because this would also follow that same sign chart, right? It's increasing, then it's decreasing, then it's increasing. And so we might only have a local max, but an absolute min, or we could do it, vice versa, where this is going down forever, hitting this, but then approaching an asymptote. And so my local min wouldn't be an absolute, but my max would be. So any of these would meet the same criteria for that sign chart. So it's all about checking the in behavior if you don't know how that function behaves as it goes towards infinity already, like you would for a polynomial function. Does that help?
Yeah, thank you.
Yeah, and then, in addition to that too, you just got to make sure that when you, this I think is this one's a little more intuitive, a little more common sense here. Like if I have say I have like a 4th degree function where I've got, increasing, decreasing, increasing, decreasing. Well, obviously I'm not going to have an absolute min. I do have a local min, but then the local maxes, one may just be higher than the other one. And so you got to just plug in the values to figure out which one is the higher one. But I feel like that hopefully answers your question fully, maybe. Good or no? Everyone all right with that?
Yeah, thank you.
Mm-hmm. Anybody else have any other questions on anything we've been talking about and working on? All right, let's get started with what we're going to do today then. So today we're going to start off with a fairly simple theorem This is called the mean value theorem for derivatives. So the mean value theorem for derivatives simply states that if you have a function that's continuous on a closed interval from a to b, and it's differentiable on an open interval from a to b, then there is on that interval at least one point, and we call it c, where the instantaneous rate of change, right, so the slope of the tangent line, is equal to the slope of the secant line between a and b, or the average rate of change on that interval. Okay, so that's the mean value theorem for derivatives. There is at least one point where the instantaneous rate of change equals the average rate of change on the interval. So suppose I drew some function that looked like this, and I said, let's look from, I don't know, from here to here. Yeah, we'll call this A and we'll call this B for now. The average rate of change between those 2 points, we could find that slope, right? Looks about like that. Well, all that this theorem says is that somewhere between these 2 points, there is at least one place where the instantaneous rate of change is the same. So where the slope of the tangent line is the same as the slope of that secant line. And in fact, on this interval, there happens to be, looks like, at least 2 different places where that is the case. So that's the basic idea of the theorem. Right? And this, this is our instantaneous rate of change. That's our f prime, that's our derivative. And then here is our average rate of change. It's just our slope, right? F of b minus f of a over b minus a. Does that make sense or no?
Yes.
What we're talking about here? Yeah, okay, cool. So that's the mean value theorem for derivatives. Important to recognize that there are these initial conditions here, that the function has to be continuous on a closed interval and it has to be differentiable on the open interval, which means we can't have, cusps going on in there. If that's the case, then it's not necessarily true. Can't have corners and no vertical tangent lines, no discontinuities. Obviously, no discontinuities because the first part of it says it has to be continuous. But good. Everyone feel all right about that? Let's see if we can do something with it here. So I just kind of mentioned this, that the hypotheses that it has to be continuous and differentiable, those conditions have to be met. So if you have something like the absolute value of x, right? The absolute value of x from, let's say, -1 to 1. What's the average rate of change? It's zero, exactly. F of b minus f of a over b minus a equals 0. Well, and there is nowhere between -1 and 1 where the slope of the tangent line is 0, is there? It's always either -1 or +1. And right here, there is no slope to that tangent line. There is no derivative at that point because it's a corner. And so we would say this one is not differentiable at 0, and so therefore we couldn't apply the mean value theorem. You guys familiar with the greatest integer function, I and t of x, or sometimes written like this, double brackets x?
No.
Anybody know what that function is? You do, you just probably don't remember what it's called. No? Nobody knows what that function looks like? seen a function that looks like this?
Yeah.
Yeah. You just didn't know that it was called the greatest integer function. It goes forever up like this and up and down like that. Greatest integer function, right? Well, if I were to take any 2 points on here, let's just say I picked from 0 to 1, the slope of the tangent line there would be, I'm going to go from 0, 0 to the point 1, 1, that slope would be 1, right? But nowhere on this function between 0 and 1 is the slope actually 1, it's always 0. And so the reason for this is discontinuous. It's not continuous on those intervals. If I go beyond, like, from 0 to just before 1. So just make sure that the function is continuous and that the function is differentiable on the interval that you're looking at. So let's do an easy one here and look at f of x equals x squared and see if this satisfies the hypotheses of the mean value theorem on our interval, and then see if we can find a solution to this equation that represents the mean value theorem. So here's the part where I asked you, what's the first thing that we should do? And then you tell me.
Is it find a derivative?
No, it's not. This is the time where it's wrong. Remember I told you, like, it's almost always going to be right? This is the time where we don't want to find our derivative first, because what do we have to do before we can take the derivative and do all that stuff? We just talked about it, right? We have to make sure that the hypotheses of this mean value theorem have been met, right? So we have to show that it satisfies the hypotheses of it, which are that the function is continuous on the interval 0 to 2. And is it continuous on the interval from 0 to 2?
Yes.
And how do we know that?
Because it's a polynomial.
Because it's a polynomial. Okay, good. And we also then have to state that f prime, the derivative, right, it's differentiable, so f prime exists on, pretend that's an s, exists on the open interval 0 to 2. And well, that's also true because it's a polynomial, because polynomial, its derivative is a polynomial, and polynomials just always exist, no matter what x values you plug in. So now we can find our derivative. What's the derivative? What is f prime of x?
Two x.
2x, which means that f prime of c is we're using f prime of c here, that's 2c, right? Needs to equal f of b minus f of a over b minus a. Everybody good with that setup there? That's our f prime at some c value that should be between 0 and 2 is equal to f of 2 minus f of 0 over 2 minus 0. Good or no?
Good.
Okay, wonderful. So now we just have to solve for c, because that's what we want to do, is we want to find the solution for c. So we still got 2c is equal to, well, what's f of 2? That ought to be
4.
4, and f of 0 ought to be 0, and then 2 minus 0, that gives us 2c equals 2, or c equals 1. So what this is telling us is that the average rate of change from 0 to 2 is the same as the instantaneous rate of change of this function at 1. And just for the heck of it, because we can, we know that the slopes of both of those lines should be 2, right? Because if we're looking at f prime of c, f prime at 1, that's 2 times 1, or 2. So the slopes are 2. One of those has to go through the point 1, 1, and the other one needs to just go through the point 0, 0, right through the origin, because that's one of the points that we just used. So this would look like y minus 1 equals 2 times x minus 1, or just y equals 2x down here for the two different lines. And if we were to graph all of this on Desmos, we've got x squared, we've got y equals x. Sorry, not y equals x, it was y equals 2x, right? Did I write y equals x? No, I didn't. Good. All right, y equals 2x, and then y minus 1 equals 2 times x minus 1, and we can see that clearly those two are parallel, which makes sense because they both have a slope of 2. One goes through the endpoints of the interval we were talking about, 0, 0, and 2, 4, and the other one is tangent to our function at 1, 1. Good or no?
So we have the green line given to us, and that's the fixed interval that we find the slope of because, like, we just find it because that's what we need to do. And then we find whatever line would be tangent and parallel to the original line that we received.
Exactly. So parallel to the original line that you won't be given the line, but you'll at least be given the 2 points or the 2 x values at which that line has to cross through your function. So you can find the points and find the equation. So yeah, we're looking for the line that has the same slope, so parallel to that secant line, that is also tangent to the function somewhere on that interval from 0 to 2, or whatever the interval I happen to give you is. Everything you said is correct. So, yeah.
Thank you.
Anybody else have any other questions on that or no? All right. So I would like you all to take just a second and look at these two functions and see if you can determine why each of them fail to satisfy the hypotheses of the mean value theorem. So you guys ready to talk about both of those and why they fail to satisfy the mean value theorem hypotheses? Or you need another minute? Okay, so for the first one, is this function continuous on the interval from -1 to 2? Can I plug every number in from -1 to 2 into this function?
Yes.
Yep, definitely, right? And the only place where something weird might be happening is where it changes from being a positive number to a negative number, but it's still continuous. So this is continuous on -1 to 2. And then what about differentiable? Well, if we look at when this is differentiable, the derivative of root x squared is 1 over 2 root x squared times the derivative of x squared, which is 2x. And when would this thing be undefined at x equals 0, right? And so that would tell us that the derivative is undefined somewhere on this interval. So this one is not differentiable at x equals 0, which is on the interval from -1 to 2. Good on that one?
Yes.
Okay, what about this one? To figure out if this is continuous at all the values between -1 and 2, the only place where it might not be is at 1. So we'd want to look at the limit as x approaches 1 from the left, which would be 1 cubed plus 3, right, which would be 4. And then we'd look at the limit as x approaches 1 from the right of f of x, which would be 1 squared plus 1 or 2. And since those don't match up, that fails the definition of continuity. So we would say it's not continuous on -1 to 2, right? Specifically, not continuous at x equals 1. Good or no?
Good.
Great. Okay. Let's, I guess, just do one more of these. Then we have a little thing to add to it. And then we're going to continue moving on to the rest of this applications of the derivative unit. So we've got f of x equals root of 1 minus x squared. We want to find a tangent to f on the interval -1 to 1 that is parallel to the secant line through there. And so we could use the mean value theorem to see if this has to exist, right? We could say that is f continuous on -1 to 1? Should be, right? We should know what this looks like already. What does this look like? What does root 1 minus x squared look like?
A turned parabola?
Mm,
A line?
no. Root 1 minus x squared. This is a graph you guys should all, if you don't know it now, you should know what this graph looks like, or root 4 minus x squared, or root 9 minus x squared. Suppose, I'm going to write this as y equals root 1 minus x squared, and I'm going to just get rid of the square root, right? That'd make this y squared equals 1 minus x squared, or x squared plus y squared equals 1. What is that graph?
A circle.
A circle, right? Yeah, so this, the positive square root, this is the top of the circle. And if I made it a negative square root, it'd be the bottom of the circle. So just to show you guys right here, right? We know that x squared plus y squared equals 1 is just a circle, right? Centered at the origin with a radius of 1. And if we have square root of 1 minus x squared, that's just the top part of the circle. And throw a negative in front, it is the bottom part. Good or no? Everybody's good there?
Yes.
All right. So we know it's continuous, and then if we were to take the derivative to see if it exists, f prime of x equals 1 over 2 root 1 minus x squared times the derivative of the negative x squared, which is negative 2x. And so the only thing that would make this undefined is when the denominator is equal to 0, and 1 minus x squared would have to be 0. And so that would be x is plus or minus 1. But since it only has to be differentiable on the open interval from negative 1 to 1, that those two values wouldn't apply. Does that make sense to everybody? And so we can say that this is differentiable on that interval. And so now we know that we're guaranteed that there must be a place on here. So there's our derivative. And let's if we simplify our derivative, we had negative 2x over 2 root 1 minus x squared. So that would just be negative x over root 1 minus x squared. And we want to know, when does that equal the average rate of change between these 2 points? And what's the slope between those 2 points? It's the two y values, right? 0 minus 0 over 1 minus negative 1. So we want to know, when does negative x over root 1 minus x squared equals 0? And that would be when x equals
0.
0. Right? And if we went back and find, if we found the slope here, the slope is 0. And so we know that that should just be for the function root 1 minus x squared at x equals 0, what do you get? You get 1, right? And so if it's got a slope of 0 at x equals 0, and it has a y value of 1, that should just be the equation y equals 1. So y equals 1 is tangent to our function at 0, horizontal line, and it should be going through, or it should be parallel to the line that goes through those two endpoints, right? Which would be y equals 0. Good or no?
Good.
All right. So the last thing about this is there's a corollary to the mean value theorem, which is called Rolle's theorem, and you'll need to know that name. And Rolle's theorem just says that if the function is continuous on the closed interval and differentiable on the open interval, and just like the one we just did, f of a is equal to f of b, then the derivative must be 0 for at least one number on a to b. Or in other words, there must be at least one critical value or one critical number, one critical point on a to b. And so what we just had here, right, we had f of a was equal to 0 and f of b was equal to 0. They were equal to each other. And so that told us there must be a place where the derivative equaled 0, right, which is what we just did. So that one was part of the Rolle's theorem, as part of the corollary to this mean value theorem. And so this is really it's an important idea that if the function equals itself at two different places and it's differentiable in between there, or equals the same value, there's no way to go from this point to this point without having at least one place in between them where the derivative equals 0, as long as the derivative is defined, right? The only way I can get from here to here is maybe like this. Let's say I do it that way. Is there a place where the derivative is 0?
Yeah.
Yep. What if I do it like this? Is there a place where the derivative is 0?
Yes.
Okay. What if I do it like this? Is there at least one place where the derivative is 0?
Yes.
Yep. There's in fact 3 of them, right? What if I do it like this? Straight horizontal line. Is there at least one place where the derivative is 0?
Yes.
Yeah, in fact, every place along here, the derivative is equal to 0. What if I do it like this? Is there a place where the derivative equals 0?
No.
No, but the reason why there isn't is because the function is not differentiable on the entire interval. Okay, so this one doesn't meet the hypotheses of it. Good, makes sense?
Good.
Wonderful. All right. So let's real quickly take a nice simple function like 4x squared minus 20x plus 29 and show that this function satisfies all three of the hypotheses of Rolle's theorem on the closed interval from 1 to 4, and then find all of the places where the derivative equals 0. So let's find all of the places where this has critical values. So what's the first thing we should do?
Prove the function fits the criteria.
Exactly. So first off, is f continuous?
Yes.
And why?
Because it's a polynomial.
Because it's polynomial. Okay. And what about f prime? Does it exist on 1 to 4? Why does f prime exist on 1 to 4?
Also because of a polynomial.
Also because it's a polynomial, okay. And so then we need to show that f of 1 and f of 4 have the same value. And so what's f of 1? F of 1 ought to be 4 minus 20, which is negative 16, right, plus 29, which ought to be 13. And f of 4 ought to be 64 minus 80, which is negative 16, plus 29, which is 13. So we've got f of 1 is equal to f of 4. And so we've now satisfied all three of the criteria for Rolle's theorem, which means we can now go in and say that the derivative of this, f prime, which is 8x minus 20, needs to equal 0. We know that it must equal 0 somewhere between 1 and 4. And all we have to do is solve that very simple equation, which gives us what? X equals 20 over 8, which is what? 5 over 2. Good or no?
Good.
All right. Wonderful. So that is really all there is to the mean value theorem itself. Anybody have any questions on that in general or at all? Everyone's good?
Good.
All right, let's see. I think we have plenty of time. Everybody feeling not overwhelmed? Like stuff we've done today has been relatively easy so far, I hope.
Yeah.
Oh, good. So we're going to take a function, x cubed minus 7x squared plus 5x plus 2. Could be any function. And we're going to pick a point and zoom in. So what did I say? I said x cubed minus 7x squared plus something, something, something.
Plus 5x plus 2.
Plus. 5x plus 2, is that right?
Yes.
Not that it really matters, but plus 2, plus 1. All right, let's pick a point. Let's pick the point here at 0, 2. All right, this point at 0, 2, and I'm going to zoom in on that point. Does this still look like the same function? It hasn't changed much. I can just see one part of it, right? But it still looks like a nice little cubic or parabolic looking curve, doesn't it?
Yes.
Yeah. What about now? Still look like this nice cubic parabolic curve? I may be missing the top of it, but still looks like it, right?
Yeah.
How about now?
Looks more like a line.
Looks more like a line. How about now and now and now and now? It looks even more like a line, doesn't it? The further I zoom in, the more it looks like a line. True? I think this is something we talked about once before, a little bit. I think I did this when we were first talking about derivatives.
Yeah.
Yeah, and we probably even noted that even if we don't zoom in, like we zoomed it in at a point where it was kind of already sort of getting to be linear, but if I zoomed in on a point where I had a local max, let's say, like right here, eventually, right, the more I zoom in on that local maximum, it stops looking like that parabolic curve, and it eventually, oh, I didn't mean to do that. Eventually, even that point where there's a local maximum starts to just look like a straight line. True?
True.
Okay. That idea is the whole sort of crux of what derivatives are all about. It's this linearization idea that if you get local enough, you zoom in, then the function, any function that has a derivative at that point will begin to look like a straight line. It's called linearization, or we sometimes call it local linearity. Linearization or local linearity. And so the function itself starts to resemble its tangent line, right? And so the tangent line of a function at some value a is just this equation, right? This is the point slope form of a comma f of a, right? At this point, right? Because its slope right here, right? Its slope is the derivative at a, right? And the point is a f of a. So y minus the y value equals the slope times x minus the x value. So this equation, which we call the the tangent line equation in point slope form, is effectively on a very small interval a very, very, very good approximation for the actual value of the function. So we're going to use that, and we're actually going to solve it for y. And we're going to write it as y equals f of a plus f prime of a times x minus a. And we're going to call this function here the linearization function. And the linearization function is just a function that can be used to approximate the value of our original function. And the smaller the interval we're looking at, the better the approximation will be. So we're going to use it for something like approximating what the square root of something like 1.02 is, right? Because we know, we know that 1.02 is very close to 1, right? And so if we were to use the tangent line to approximate the square root of this on a very small interval, it's very easy to figure out what this linearization equation is. If I have a function and that I can find that function's derivative, it's really easy to approximate this without a calculator, but it's not so easy to just sort of figure out what that is without a calculator. that make sense? A little bit?
Yeah.
Okay. So our goal, and one of the things that's really important about derivatives, is that we can use them to approximate the values of functions. And so we're going to use this function here, L of x, which is just what I had on the previous page, and we're going to call that the linearization function. Okay? It's the standard linear approximation of our function at some value a. And so we call this value of a the center of approximation. And the center of approximation is just the value of x that we could plug into our function that we're using that we know the value of it already. So in this case, our I'm going to sort of written this poorly probably here. We're going to say at a equals 0, right? We're going to use a equals 0 because if I plug in a 0 for this x, that would tell me that this is the square root of 1, which I know how to evaluate, right? We know what the square root of 1 is. So a is always the value that you plug into the function that you know the value of it already at. And then our x value is our new value that we want to use that has this extra little bit added in. Does that sort of make sense or no?
Yeah.
Okay. I think that if it's a little confusing to you at this exact moment, that's okay. I think it's going to hopefully make more sense as we sort of go through it. So we want to find the square root of 1.02. That's our goal. We want to approximate it without using a calculator. And so we're going to use the function f of x equals root 1 plus x. And so like we said, we want a to be 0 because we know what the square root of 1 plus 0 is. That tells us that our x value should be just 0.02, because if x is 0.02, that gives us the square root of 1.02, which is what we're looking for, right? So what we would do is we'd write something out like this. We'd say the square root of 1.02, that's f of 0.02, isn't it?
Yes.
Yeah. So what we'll say, that is approximately equal to the linearization function at 0.02. And our linearization function is this one right here. So the linearization function is f of a. What's f of a? That's the square root of 1 plus 0 plus f prime of a. Well, if f of x is 1 plus x, what's f prime of x? It's 1 over 2 root 1 plus x. Right, using the chain rule there times the derivative of 1 plus x, which is just 1. So what's f prime of a? Well, it's 1 over 2 root 1 plus 0. And then times x 0.02 minus a minus 0. Good so far or no?
Yes.
All right, so now all we do is we just plug in and evaluate all this stuff. Square root of 1 plus 0 is just 1, right? And then this is 1 over 2 times 1, so that's a half of 0.02. Which gives us what? 1.01, right? True or no?
True.
Okay. And you're probably sitting there thinking, like, what kind of stupid crap is this? If somebody asks me, what's the square root of 1.02? And I'm just going to be snotty to them. I'm like, I don't know, 1.01, right? Because you're just like trying to come up with something that you know is a little bit less than 1.02, but if you know it's got to be more than 1. So this doesn't sound like a very good approximation for the square root of 1.02, probably. It just kind of sounds like some crappy answer that you guessed. But if you take your calculator and actually evaluate what is the square root of 1.02. Somebody do that for me.
1.0099.
1.0099. So 1.0099 is pretty darn close to 1.01, isn't it?
Yes.
Yeah, and so we could say that this is actually a pretty darn good approximation. I mean, this is 1 and 1/100th. Well, this is 1 and 99 10,000ths, right? Which is, I mean, only off by 1/10,000th from this actual value. And there was probably more to it, right? It was 1.0099 what?
0.5 something.
0.5 something. Yeah. So we're off by slightly less than 1/10,000th with this approximation, which for pretty much any calculation and measurement that you're trying to do is going to be more than good enough, right? Let's see if we can do this with a different function. Let's see if we can do this with the cosine function, the cosine of 1.75. So we want to know the cosine of 1.75. And so that should be f of 1.75, right? Which should approximately be equal to the linearization function at 1.75. So the x value that we're looking at is 1.75. And 1.75 is very close to pi over 2. So we're going to do what's called centering our approximation at pi over 2. That's the value that we know the cosine of, right? We know what the cosine of pi over 2 is, don't we? Oh,
yeah.
Yeah, right. We should know. Yeah, I mean, we should know what it is. Right? Cosine of pi over 2 is 0. And so all we have to do then is figure out what the derivative is. What's the derivative of f? Should be negative sine of x, right? So we can plug in 1.75 into the linearization function. And our linearization function, once again, is f of a. So f is cosine, so that would be cosine of a and plus f prime of a, so negative sine of pi over 2, times x minus a. Good or no?
Good.
Okay, cool. So now let's approximate this all out and evaluate it. So cosine of pi over 2 is 0, we already said, right? What about the sine of pi over 2? That's 1 times a negative. That's a negative 1. So really what we're doing is we're taking a negative 1 and distributing it through there, which ought to give us 0 plus pi over 2 minus 1.75. And so what we're saying here is that an approximation for the cosine of 1.75 is pi over 2 minus 1.75, which also seems kind of absurd, like an absurd thing to say, right? Well, the cosine of 1.75 is about pi over 2 minus 1.75. Well, what is pi over 2 minus 1.75 approximately? Give me as many decimals as you can.
Negative 0.17920367732.
All right. And now tell me on your calculator what actually is, using your calculator, this value for the cosine of 1.75, making sure that you're in radians.
Negative 0.17824605556.
Right. Which we can see that's pretty darn close again, right? It's off by this time about 1/1000th, right? Negative 0.179 to negative 0.178. It's a pretty darn good approximation. Wouldn't you say?
Is it always going to be a similar difference between the actual and the approximation?
I mean, between these two, yeah, it should be very, very close, because that's kind of the whole point of it all, is we're trying to get something that's exceptionally close to the true value. And so this approximation should be generally, as long as it's the number we choose is pretty close, it should be within 100th or less of the original value.
Okay, got it.
And I mean, we even, we think about it, what's the difference between pi/2 and 1.75? I mean, this last one that we did, right? We differed by 2/100ths, and we got a value that was pretty darn good. Well, even here, we were fairly far away. The difference between pi/2 and 1.75 is, I mean, it's 1700ths. That's a lot more than 200ths, but we were still only off by 1/1000th from the actual value, which is pretty good, I would say. So let's see if we can use this idea to come up with an approximation for the square root of 26. What would the function that we are looking at here, what would f of x be? What function is the square root of 26? It's using a square root function, isn't it? So how about square root of x? Yeah. With x equal to 26, right? Where should we center this approximation? What's a number that's pretty close to 26 that we know the square root of?
25.
25, right? So we'll center this at 25. And we're going to need the derivative. What's f prime of x? That should be 1/2 root x. And so we then should be able to say that the square root of 26 is f of 26, which should be approximately equal to L of 26, which ought to be f of a, so square root of 25, plus f prime of a, 1/2 root 25, times x minus a. Good or no?
Good.
Good.
All right, and so we should then be able to say that square root of 25 is 5. Once again, square root of 25 is 5, so this is 1/10. So 5 plus 1/10 times 1, or 5 1/10, 5.1. And this is another one of those cases where it kind of sounds like you're just making up some crappy answer to be snotty to somebody who's like, what's the square root of 26? You're like, I don't know, 5.1. Well, according to your calculator, what's the square root of 26?
$5.099019514.
Yeah, 5.09901. So really we're off by, I mean, that's 1/1000th. We're off by a little bit less than 1/1000th again. So it's a pretty good approximation. Good or no?
Good.
All right. We're going to stop there because we are almost out of time. Anybody have any questions before I cut this off, stop recording it?